Thank you very much. Maybe before I start, I just wanted to correct something on the website regarding the talks. We just switched with Maximilian, so it will be me again speaking on Friday, and Maximilian will start his talks on Monday. All right, so on Monday I somehow explain what is like the geometric framework in which we will be working. So I introduce this category of stacks on. First I introduce this category of Gelfand rings, and endowed with a Schrick topology, and having as a nice basis a subcategory of nil perfectoid ring. And stacks on this category is what we call Gelfand stacks, and I explained that this contains the geometric objects we care about, so Dagger rigid spaces, or more generally Berkovich spaces. And then I give this example of the RAM stacks. So the goal for today is to define the rational analytic prismatization of rigid spaces, or more generally Berkovich spaces. And so here the adjective analytic is here to stress that, or to distinguish this construction I will explain from the already existing definition of prismatization by Bhatt, Lurie, and Drinfeld. But I don't think this really can be the source of any kind of confusion, because the geometric objects for which I will define this prismatization is like living in characteristic 0 over QP, so these are rigid spaces. Whereas in the theory of Bhatt, Lurie, and Drinfeld, one always starts with p-adic formal schemes. So I will just drop this adjective. And this one is maybe more important. So I want to stress that in this talks, and also in the talks by Maximilian, we will not somehow be discussing really the full picture. First of all, the geometry is in characteristic 0. One could be more general and also allow like some kind of analytic spaces over ZP. But also the coefficients will be rational. So this really means that I will only define the QP fiber of what should be the true analytic prismatization of rigid spaces. So I have both a restriction to QP in the geometry and in the coefficients. But probably I will also just stop saying rational very quickly. Yeah. But you should keep in mind that this is what we are going to do is just part of the picture, which is sort of simpler than the general case. And we may see, if we have enough time, we may see at the end of this series of lectures a little bit what should happen if we try to work integrally. Okay, but so maybe before getting to the definitions, let's maybe just remind ourselves how the theory of p-complete prismatization works. And maybe I just want to explain one thing. So prismatic cohomology was first defined by Bhatt and Scholze using the prismatic site. So you define a site and a certain kind of structure shift on this site, and prismatic cohomology is cohomology of the structure shift on the prismatic site. But later on, Bhatt, Lurie, and Drinfeld have defined the prismatization of a p-adic formal scheme. And just, it's maybe, when you see it the first time, not so clear so obvious how you pass from the prismatic site to the prismatization. So let me, because this will be useful, we'll then mimic this in the rigid analytic case. Let me just quickly explain some kind of slightly oversimplified picture for how to get how to get the definition of the prismatization once you know what the prismatic site is. So once you know what a prism is. And one way to think about it, I guess there are different ways of motivating this, is, so let me write ZP prism. So that's not really a standard notation for the functor which on the category of like p-complete delta rings. And maybe here, again, like everything is supposed to be taken animated to anima, which sends such a p-complete delta ring to anima of prismatic structures on A. So generalized Cartier divisor on A, which define a structure of a prism on A. And yeah.
There's some, I mean, if you say it this way, then there's some potential issue that if you have a map from A to A prime and like A is iadically complete.
Yeah, that's why. Okay, yeah, I don't want to be completely. I completely agree with you. One has to be. Yeah, there's this issue with completeness that shows up. I totally agree, but that won't really be the case in our setup. So that's why I want to somehow gloss over these subtleties. But yeah, actually, it's totally right that. Well, first of all, it's important to work animated if you want, like, derived, if you want to be able to base change. But then you still have the problem that in the definition of a prism, you require some kind of p-adic, pi completeness condition that is not automatic when you do a base change. So yeah, that's. I'm slightly cheating here. But so okay, so that. So let me look at. So that's one definition you can make. And now let me look at stacks on delta rings. So when I say delta rings, I always implicitly assume that they are p-complete. And I maybe also don't want to really specify which topology I work with. Let's say, for example, étale topology. So we have a functor from stacks on delta rings to stacks on p-nilpotent ring. Sorry, here I want to look at stacks on delta rings which lives over ZP prisms. I will just, this functor I will define just to be the left-can extension of the functor which would send delta ring A together with a prismatic structure, which is what my morphism from sphere A to ZP prism give me by definition of ZP prism. And then I send this to the formal spectrum of A mod I. So that's a colimit preserving functor, which has a right adjoint. Which is a functor which I will denote X prism. That's again not standard notation. So it will be a functor on delta rings over ZP prism. And what it does, it's, well, by definition, because it's defined as a right adjoint, it's just. Okay, and maybe side remark is that the prismatic topos of X, as defined by Bhatt Scholze, would be really just a slice of the category of stacks on delta rings over what I denote by explicitly. Okay, and so that's basically what the prismatization is. You just upgrade your, realize your p-adic formal scheme X. So here, maybe I should have said, so X is a p-adic formal scheme, probably, or more generally a stack on, let's say, we care about p-adic, prismatization of p-adic formal schemes. And you just upgrade it to a functor on delta rings over ZP prism. But really, maybe the prismatization as you know it is like, it's again a stacks on phi-nilpotent rings. So to recover this, let me observe that there is another functor from no define really on the category all stacks on delta rings to stacks on p-nilpotent ring again, which now is just, again, colimit preserving and sends well, let me write like something like delta spec. So it's just the functor on delta rings co-represented by a delta ring A is just sent to the formal spectrum of A. So now it's it's basically just the functor from delta rings to rings, which just forgets the delta structure. And that's a functor I want to call the realization functor. And then really the prismatization as defined by, well, up to various subtleties and approximations, it's really just what you get by taking this stack on delta rings, X lower prism, and taking its realization. And why is that? Well, basically because this realization functor has itself a left adjoint. Which is simply the functor which sends, so it's left adjoint, so it should go, sorry, what am I trying to say now? No. I'm sorry, I'm getting myself confused. Yeah, okay, yeah, which sends R, P nilpotent ring to, well, the functor on delta rings co-represented by the Witt vectors of R. So concretely, that means that this you can just compute as by evaluating this X lower prism. If you have a P nilpotent ring R, what's the evaluation on this of this X upper prism on R? It's basically just you take this X lower prism and evaluate on the Witt vectors of R. So you are just looking at a prismatic structure on the Witt vectors, which is basically what a Cartier-Witt divisor is. That's also not quite true, but almost. And then you just, by definition of this, you just take the reduction modulo the ideal. So then you recover the formula of which defines the prismatization in the work of Bhatt, Lurie, and Drinfeld. Okay, so that's some of the pattern I want to mimic. I will try to, so what I will do now is I will define the analog of a notion of delta ring in our setup, and then the notion of a prism. And then we'll have a very similar mechanism that we will have some of these two functors from stacks on delta rings, on this analytic version of delta rings, to Gelfand stacks. And we will play with this adjoint and define the rational analytic prismatization in this way. So that's what I want to do now, step by step. Okay. Any questions about that before I start? So I can also write here. Yeah, okay. Okay, so so let me start by first some brief recollections on Fark-Fontaine disks and Fark-Fontaine curves. This is mostly to set notation. So yeah. I want to slowly get to the definition of a delta ring, but I will make some definitions which will at first maybe look totally unrelated, but we will see how to see the analogy a bit better later. So these are constructions which are due to Fark and Fontaine. So they take as an input perfectoid spaces of, let's say, affinoid. So, okay, I try to work always in the Berkovich setting. So instead of writing SPA, I will just write M. So A is some affinoid, some perfectoid ring of characteristic P. And let's var pi be a pseudo-uniformizer of A, i.e. a topologically nilpotent unit. And again, a perfectoid for me always means a Tate perfectoid. And so now there is this definition of, so define the Fark-Fontaine disk of S, which I will denote dff of S as, so you take the Berkovich space with vectors of the power-bounded element in A. So that's some affinoid Berkovich space. And then you remove the locus where a Teichmüller of the pseudo-uniformizer vanishes. All right, and then there is also the what you may call the punctured Fark-Fontaine disk, and we will denote it by like this with a star. And there you, in addition, also take the generic fiber, so you also remove the vanishing locus of P. Okay, so yeah. So these are some kind of like Stein spaces, because you have, like the usual picture is something like this. So that would be the vanishing locus of P. That would be the vanishing locus of Teichmüller of var pi. And so you are only looking at, so you remove these two divisors and you only look at what happens here. And so, but.
These are also called Y, is that right?
Yeah, that's going to be my next remark. So maybe a more standard notation for these objects is, this is sometimes in the literature also denoted Y0 infinity S, for a reason that will be a bit more clear in a minute. And this, this would be Y0 infinity open at 0 as well, S. That's also, that's not the notation I'm going to use, but that's a maybe more standard notation. And the reason why it's called a disk is because basically if you would replace the local field QP by a local field of positive characteristic, then this would literally be disk on punctured disk relative to the perfectoid base S. Okay, so maybe a useful observation is that there is some radius map. So there exists a map kappa from the disk, Fark-Fontaine disk relative to S, to the interval 0 infinity. So when I write such a thing, this has to be understood as like really that's a topological space. I take its Betti stack and seen as a Gelfand stack, and this is a Berkovich space, which I also see as a Gelfand stack. But to keep the notation simple, I won't write this subscript Betti. And basically, this map is obtaining by, on your Berkovich spaces, which moduli parameterize these norms, or semi-norms, you just compare the norm of var pi and Teichmüller of var pi and the norm of P. So kappa is defined by, at least on the underlying topological space, it's like it sends x to, the formula is, so minus log so my point x in this Berkovich space corresponds to a norm, which I denote like this. And then, let me get this right, over log of, I hope I got that right. And so when P vanishes, corresponds to the case where kappa is 0. So in fact, kappa, the inverse image by kappa of this open interval 0 infinity is exactly my punctured Fark-Fontaine disk.
So just to clarify, which category are these objects D and D cross living in?
These are Berkovich spaces, but I can see them as Gelfand stacks.
Okay. Well, sorry, I guess the first one is not over QE, so right,
that's right. Yeah, okay. Let's say analytic stacks, then, yeah, you're right. But okay, I will very quickly just focus on D star and then see everything as Gelfand stacks. But yeah, you're right. Yeah, it defines only Gelfand stacks over QP, so that's, yeah. Yeah, okay. And just one more small remark about this radius map, kappa. A priori, it depends on this choice of a pseudo-uniformizer. But in practice, in what I will do in the following, S will always be of the form T flat, where T is a perfectoid space in characteristic 0. And if T is living over, so T lives over QP, but if it's in fact living, if it contains like a compatible system of p square roots of unity, I can just take my var pi to be given by this compatible system of p roots of unity. So p flat is like p root of p square roots and so on. And okay, that's again a choice. But if you take two different such compatible systems, they just differ by a norm one element, by the compatible system of p roots of unity. So this is not affected. And then this also shows that this will in fact descend to QP. So if your S arises as a tilt of something in characteristic 0, there is a rather canonical choice of this radius map. And this is what I will implicitly always do in the following. Okay.
So is it correct that whenever you have a Berkovich space, you can regard it as, well, maybe, so this is outside classical Berkovich spaces, right? But if you have sort of generalized Berkovich space, you can see it as a Gelfand stack in your setting, and there's a natural map from the Gelfand stack to the underlying topological space of the Berkovich space.
Yeah, that is right. There is a natural map from the Berkovich space in as a Gelfand stack to the Betti stack of the Berkovich spectrum. That's right. Yeah.
And this is, well, part of that. It comes from.
Yeah, exactly. That would somehow factor through this. Yeah, that's true. Okay, and another observation is that this Fark-Fontaine disk and also punctured Fark-Fontaine disk, they are both endowed with a Frobenius, which is coming from the Frobenius on S, the Frobenius on the Witt vectors. And when you remove the locus where P is 0, this action of Frobenius acts properly totally discontinuously, so you can define what is called the Fark-Fontaine curve relative to S as the quotient of so Frobenius I will denote by phi, and the quotient by this Frobenius action is what is called the relative Fark-Fontaine curve over S. Although these spaces don't live over S because these two lives in characteristic 0, they live over QP. Okay. And then one more remark is that these spaces have a really nice and simple description after you pass to the perfectoidization. So applying perfectoidization, so because I only defined this for last time for arc stacks over QP, let me maybe Gelfand stacks, let me maybe just restrict to the example of the punctured Fark-Fontaine disk, but there is an analogous formula for the whole disk. This is just given, when I take the perfectoidization, this is just given by S times the arc stack of QP. Fiber product taken over the arc stack of yeah, so even though this does not literally live over S as a Berkovich space, when you take the associated arc stack, then you do have a map to S. Okay. Right, now let me state a lemma that I will use a bit later. I won't prove it. The proof is really just an exercise based on what I explained. So the lemma says, if you have a perfectoid space X over QP, with tilt given by T flat, and then any morphism of Gelfand stacks from T to, why did I write T? I meant to write X. From X to the Fark-Fontaine disk of Y, where Y is a perfect Witt space in characteristic P. Any such uniquely extends to a phi equivalent morphism from so like that. So you have here the punctured Fark-Fontaine disk for X flat. Where this morphism here arises from a morphism of perfect Witt spaces in characteristic P by functoriality of this construction of punctured Fark-Fontaine disk. And here, this map here that I'm using is just corresponding to the untilt. So this Fark-Fontaine disk parameterizes untilts for a perfect Witt space in characteristic P, parameterizes untilts of it in characteristic 0, and here by a choice of X flat is naturally the tilt of X, so this is just corresponding to the untilt X of X flat. Okay, so whenever I have such a map, I can actually extend it to a map from the punctured Fark-Fontaine disk for the tilt in a Frobenius equivalent way, such that my original map is recovered as this composition. And yeah, so I leave this as really an exercise based on Okay, so I will need this lemma a bit later. Okay, and another remark is that this construction associated to a perfect Witt ring in characteristic P, its relative punctured Fark-Fontaine disk, it satisfies nice descent property. So the functor sending A to D star FF of, S, which is M of A, on perfect Witt spaces of characteristic P. It sends R cover and even hypercovers of perfect Witt spaces in characteristic P to Schrick covers of Gelfand stacks. And so because of this, you can extend it to a co-limit preserving functor from the category of arc stacks to the category of Gelfand stacks. And the notation I will use is the same, so I will just write it like this. Okay, so for this to be really correct, you have to put some assumptions on your perfect Witt rings. So this kind of countability and finite dimensionality assumption that I already mentioned on Monday. And also you really have to consider hypercovers here and some kind of, this correct notion of the correct class of hypercovers you use in the definition of Gelfand stacks, but this you can do. And then you get this construction. So maybe I should stress, and also you could also take the quotient by Frobenius and get the construction by. But maybe I should stress that this is not remark. What you always have, so you have that. So if you have X on arc stack, sorry, so maybe what I want to say is that if X is an arc stack, in general, it's not true. So you have a map, a natural map from this punctured far content this over X. So that's a Gelfand stack. So you can take its perfect utilization. Now you get an arc stack over QP. And last time I explained that there is that this perfect utilization functor has a left adjoint, which I denoted like this. And so you have a natural map like this by adjunction, but this is in general not an isomorphism.
Can I think of this statement you wrote down that it sends arc covers to Schritt covers as something like I have some V cover of usual perfectoid spaces, and then I have some descent result for vector bundles on the Fark-Fontaine curve, or
yeah, it's something like it's exactly that. But for maybe for all quasi-coherent shifts. Yeah.
It was with. Could you say again the assumptions you need? You need some.
Like this notion of what we call like separable, so some countability assumptions that says uniform completion as a countable basis as a Banach QP algebra, and this QFD condition, quasi-finite dimensional. So it's again purely condition on the uniform completion, that it is quasi-proetal over some affine space, some finite dimensional affine space. But you could also restrict, if you like, you can also restrict to strictly totally disconnected perfectoid rings, and then this is fine. But basically, these QFD assumptions are exactly there to ensure that you can always find a Schritt cover of such rings by strictly totally disconnected ones. So that's okay, and this maybe is a very technical remark, but just to stress that here we really did some, like this Fark-Fontaine disks themselves are not quite perfectoid. And so if you look at this formula for the associated diamond, this product formula, when I do this construction, I'm really just doing like some kind of arc descent in the variable S, not in the other, not on the QP factor, so to say, if that makes sense. So same for passing to quotient by Frobenius, you also have a natural map like this. This is not in general an isomorphism. So yeah, that's Fark-Fontaine curves will play an important role in the following, and I wanted just to stress this to avoid potential confusion, because typically my X could be of the form Y diamond for some rigid space Y, for example. So then you really have to distinguish between, you have to be careful where I put this diamond symbol, where I put it here in the bottom or I put it on top. And this will be different objects. So something like Fark-Fontaine Y diamond, as I just defined it, is a Gelfand stack. But if I put it on top, it would be an arc stack. So, yeah, sorry for the maybe not optimal choice of notation. Okay, so based on this, I can finally define, speak about delta rings. So you have to think about the following definition as something like analytic delta rings, but only like the version with some, so to say, with QP coefficients. But they are not really rings, they are really spaces. They are not affine objects. So that's why we call them delta space and not delta rings. So rational, again, this rational adjective refers to this restriction, and I will just drop it in what follows. Delta space is the datum of, so it's a S curly x iota on phi of x, where so S is a perfect fluid space in characteristic P. X is a Berkovich space. So in this generalized sense, which like also allow like derived Berkovich spaces. Iota is a morphism from, so it's always over QP. So it's a morphism from the Fark-Fontaine disk relative to the punctured Fark-Fontaine disk over my perfect fluid space S to curly X. And which is such that when I pass to apply this perfect fluidization functor, this becomes an isomorphism. And phi is an endomorphism of X, which makes this morphism iota Frobenius equivariant. Okay, so that's what I want to be an analog of a delta ring, and I will explain why this is maybe a reasonable analog definition compared to the usual notion of a delta ring later. And okay, you have a notion of a morphism of such. So it's a morphism. I guess you can guess the definition. So a morphism between. So first of all, let me in the following always just to keep notation simple, just abbreviate the notation. I will just write the first two variables and always drop the iota on the Frobenius. So a morphism between two such delta spaces is, well, it's a morphism of perfect fluid spaces, alpha in characteristic P, a morphism of derived Berkovich spaces, which is phi equivariant. That's a datum. And such that, well, the following diagram commutes. So you want some compatibility, of course, with iota. So alpha induces, by functoriality of this Fark-Fontaine disk construction, it induces a morphism, which I will again denote by alpha on punctured Fark-Fontaine disk. And then you have iota and iota prime, and well, you want this to commute. All right.
Park, could you move the board a bit upper? It's hiding the scene.
Yeah, sorry. That's good.
Yeah.
Okay, and finally we say that a delta space S, X is said to be perfect if Frobenius on X is an isomorphism. Okay, for notations, I don't think I will use this notation very much, but let me write space deltas for the category of rational delta spaces, and similarly maybe perf.
Phi x is what you denoted by phi on that board.
Yeah. Sorry. Yes, indeed.
And generally, just onto?
In general, there is no assumption in general.
No assumption.
Okay. So that's my definition of an analog of a delta ring. So if you want some examples, so, well, first of all, sort of stupid example is what we call like classical delta spaces. That's the case where you just take this, iota is just an isomorphism. So you just take S something of the form S and the punctured Fark-Fontaine disk over S, where iota is just the identity. So that's an example of a delta space, even a perfect delta space. And this subcategory is, so that's a subcategory of delta, of the category of perfect delta spaces, which is just equivalent to the category of perfectoid spaces of characteristic P. Another way to construct perfect delta spaces is just by taking, basically you can, if you are perfect, Frobenius is an isomorphism, so you can just quotient by Frobenius. And what you can do is you can take like a dagger sequenings of perfectoid, like of let me write perfectoid Fark-Fontaine curves. So Fark-Fontaine curves over perfectoid spaces, and then that gives you also examples of such of perfect delta spaces. So because there are dagger sequencing when you pass to the associated, when you apply the perfectoidization functors, the difference between the two disappears. So that's maybe some kind of intuition you can have in mind that these delta spaces are some kind of dagger sequencings of like relative of punctured Fark-Fontaine disks, which are like compatible with Frobenius. But that's not always the case. Another, for an example which is not of this form, which is a bit analogous to the Q-Durham prism, you can take S to be just a perfectoid space, the following perfectoid ring of characteristic P. And then this D star FF of S is just the open pre-perfectoid unit disk over QP. So it's like you take the open unit disk over QP and you extract p suits of coordinate, and then I can define my X to be just, so I will call it X cyclotomic, and I will refer to it as a cyclotomic delta space later. So it's like the limit of, it's the same thing, but this limit is now computed in Gelfand, in Berkovich spaces. So it's a limit on this raising to the P's power of 1 plus, so let's look at this, and then I remove 1. So removing 1 amounts to removing like this vanishing locus of P. And yeah, so I have a natural map from D star, that will be my iota, D star FF of S to X cyclotomic, which is just basically taking the uniform completion of this one. And yeah, because it's passing to the uniform completion, after I apply this perfectoidization functors, they become just the same thing. But this map is not really a dagger sequencing. So that's an example that I will use later. So that's an example of a perfect delta space. Okay, so now I state an important proposition which will give us many more examples of delta spaces. So that's a proposition. So I start now from a nil perfectoid ring. So I define this only over QP. And I write T for like associated Gelfand stack. And so the claim is that this category of delta spaces over T, so the category of rational delta spaces S, X with a map from T to X. This has an initial object. And this initial object has an explicit description. So maybe this initial object, I write it T flat curly xt, and it's given as follows. So T flat is just, I can take, so I can take my A, it's nil perfectoid, so it's uniform, uniform completion or dagger reduction, as you like, is a perfectoid ring over QP, and then I can tilt it. And then I take the corresponding perfectoid space in characteristic P. That's my T flat. So that's my S, if you like. And what is X? So Xt is a Berkovich space which is obtained as a certain push-out. So to make sense of this push-out, let me maybe first observe that we have in particular a map from T bar, which is G spec A bar, to because T bar defines an untilt of T flat by construction. And it gives rise to a morphism F. So this is, let's call this F. It extends to a Frobenius equivalent morphism from natural numbers times T bar basically just by the restriction here. If I take a natural number n, and then that will just be the composition. So this here will just be given by composing my F with the nth iterate of Frobenius. Okay, and now my xt is a Berkovich space, which is a push-out in Berkovich spaces of F phi from n times T bar to my contour disk, and just the natural map from n times T bar to n times T. And you have a similar result if you instead consider perfect delta spaces. The same for perfect by replacing in the above description, I just replace the natural numbers by Z. And maybe I don't want to give a notation to this perfect version because I won't really use it. But I want to give a name to the quotient by Frobenius of this initial perfect delta space. And this I will denote Farg Fontaine of T. Okay? I hope this is a bit quick, but I hope this makes sense. So I have an initial perfect delta space so that the underlying Berkovich space receives a map from T. And the quotient by Frobenius of this Berkovich space I call Farg Fontaine of T.
So just in the analogy with sort of classical delta rings, these are more like delta rings that are. It seems like these are delta rings that are not that are, for example, something like thickenings of perfect delta rings. Yeah,
let me come to make a remark in maybe 5 minutes about this too. So let's indicate the proof of this because it's not that difficult. So
can you repeat what this quotient by Frobenius?
So you have an initial delta space, a perfect delta space, such that with the property that the underlying Berkovich space receives a map from T. So same statement, but replace this category of delta spaces by perfect delta spaces. And I say that the statement is exactly the same, just replacing n by z everywhere. And then this initial object, the underlying Berkovich space, has a Frobenius, which is an isomorphism. I take the quotient by Frobenius. I call this Farc-Fontaine of T. That's a definition, or a notation. Which is, of course, compatible with if A was perfectoid, then this would just be the Farc-Fontaine, the construction we already know. Because you see that if my A is perfectoid, then T is the same as T bar, so I'm really not doing anything in this push out. So the proof is just a consequence of this lemma we had before. So if I have Sx, a delta space with a map from T to X, to curly X, well, then you can observe that T is perfect. Okay, so in particular, I get a map from, by composition, I get a map from T bar to X. But T bar is the same as passing to the corresponding diamond and then applying this hat functor because it's perfectoid. And so really a map from here to here by adjunction is the same as, it's really the same just as a map from the diamond to X diamond, which by iota is just identified with the disk over S. And so you see that, in fact, this composition, this will imply that this will factor through, by iota, through the relative Farc-Fontaine disk over S. Okay, but now I can apply my lemma from before. I apply it to X being T bar, and Y is S. And so I get an extension of this morphism to precisely from the relative Farc-Fontaine disk over T flat, which is phi equivariant, and induced by a morphism from T flat to S. Right, so already we get our map from T flat to S. All right. Okay, but now I can also just extend this, because this is endowed with a Frobenius, so this also just extend to extends to by the same recipe as the one I gave above, factoring through this Farc-Fontaine disk of T flat. And I also have an extension of Frobenius equivalent, so extends to a Frobenius equivalent map. I also have, because I have my map, I started with a map from T to X, I can also extend this to a phi equivalent map from N times T to X. Okay, and so when you put everything together, you see that so you have your map from this punctured Farc-Fontaine disk over T flat to X. You have a map from N times T to X, and they are compatible in restriction to T bar. So you get a map from the push out N times T, push out over N times T bar. You get a Frobenius equivalent map like this. But this was by definition what I call Xt. Okay, and so you have your map T flat to S and your map from Xt to X. So you have produced a morphism of delta spaces from this delta space from the proposition to your S6. Okay, so that's basically that. Okay, so here, implicit in this is maybe the claim that this push-out makes sense in Berkovich spaces. But that's basically because one of the map is a closed immersion and the other one is a dagger thickening, so you can check that this kind of push-outs exist in Berkovich spaces, and locally on rings, it's really just given by the fiber product of rings. Okay, so let me maybe make a small picture of what this looks like. So note that this xt, this Berkovich space, curly xt, it has the same arc stack as the Fark content disk over T flat, and so in particular they have the same de Rham stack. But this means in particular that this morphism, this radius map kappa on this punctured Fark content disk, they naturally factor through the de Rham stack. And so this means because of this identification of the de Rham stacks, I have a natural map, a radius map like this, from here to 0 infinity. Okay, just by projecting, using the map to the de Rham stack and this identification and the kappa map that I have already defined before for Fark content disks. And that allows you to make a picture of, well, very basic picture of what this xt looks like. So here you have your radius map. So that's your interval 0 infinity here. So that corresponds to infinity, that corresponds to 0. And I both exclude them. And then you have, okay, 1 is somewhere, and then this is 1 over p square. Here p square, and so on. And like Frobenius is moving in this direction, and like sending 1 over p square to 1 over p, then to 1, and so on. And so, so almost everywhere this xt just looks like this relative Fark content disks, but it will be like thickened just along the non-negative Frobenius translates of. So here you have, what you will have is a copy of G spec A, which is what I call T. Here as well, and so on. But here before, for the negative Frobenius translates, you really have T bar. Okay, so everywhere apart from this, okay, I don't have color, but the only locus where this xt differs from this punctured Fark content disk is just on this non-negative Frobenius translate of this copy of T. Okay, so before you keep just this until T bar and it translates, but after 1 you start modifying them. And away from that, it's just the same as the Fark content disk. So you have just done a thickening in a Frobenius equivalent way at one specific degree, one divisor. Okay, the next remark is to relate this, maybe related to Akhil's question. The idea is that you should think to the functor T goes to T flat xt, should be thought as being analogous to as a functor R goes to WR in the usual theory of delta rings. So at least it will play exactly the same role, in the sense that you see, okay, it's not defined, and contrary to this functor, which makes sense for any like p-nilpotent ring, say, this one, to construct it, we had this restriction that T is nil perfectoid, so it's only maybe a partial adjoint. But you see that by this, what the proposition is telling you is just that this defines more a left adjoint of this forgetful functor, just remembering, sending a delta space to the underlying Berkowitz space. That's what this proposition is saying. And because we work with spaces, it's a left adjoint, whereas here this would be at the level of ring, this is a right adjoint to the forgetful functor from delta rings to rings. But there is, in fact, a way to write this construction in terms of Witt vectors. So you can make this analogy a bit more precise. So again, let A be nil perfectoid over QP. And then you can do the following. I want to take the Witt vectors of the power-bounded part, as defined last time. But I will modify slightly this construction. So I introduce something I call W prime. So you take Witt vectors of the power-bounded. So this is a ZP algebra. And then you map this to the reduction. And here, what you can do is you can take the Frobenius perfection here. So take the limit under Frobenius of this. But this one is a perfectoid ring, and that's really, when you look at like a complete Huber rings, this power-bounded part is really what you think. It's what you would be usually denoted with a circle. So it really corresponds to power-bounded elements. So here you can rewrite this as this. And then here you put Witt vectors of, you can somehow put the Frobenius inside and you get Witt vectors of the power-bounded part of the tilt. So let me just write that. So that's the usual A-inf construction associated to A that you see here. And what I want to say is that this xt that I have described before, it's really its functor of points description is a functor which sends B. So B, a Gelfand ring, is sent to maps, the anima of maps from this W prime of A less or equal to 1 to the power-bounded part of B, such that, well, now I want to impose a condition that you stay away from the vanishing locus of P and the vanishing locus of Fleischmüller of P flat. That's because, as I said, we work rationally both in the geometry and in the coefficients. And so one way to say it is that such that for any composition like B to C with C is perfectoid, the composition factors through when you take spec would factor through this. What do I want to say? A bar. So I won't really give complete details about that. So I claim that this is the same as xt as I defined it before. And let me just say what the key point is. So here the key is that A is nil perfectoid over QP. So when I look at these Witt vectors, or rather maybe this W prime, this modified Witt vector, so I have this map to W of to the A-inf construction. So W of this thing by definition, and the fiber will be given by a product of well, basically by W of the dagger nil radical. Right, so I have power-bounded elements of A mapping to power-bounded elements in the dagger reduction, and then I take the perfection by Frobenius on this factor, and like the kernel would be, the fiber would be given by Witt vectors of this dagger nil radical. But now this dagger nil radical is, so that's basically the elements, power-bounded elements in A, which are infinitely divisible by P. So it's a QP module. And that's really where I'm using that my A starts life over QP. So it's this pseudo-uniformizer is really P. if I had I could make sense of the notion of a nil perfectoid in mixed characteristic, but then the nil radical would be formed by elements which are divisible by arbitrary powers of the uniformizer, which may not be P. And the fact that it's a QP module, it tells you that by Gauss components, it just identifies with the product of copies, countable product of copies of this Zeiger nil radical. And so you see that this is, here we have the usual A-inf construction, which is basically what appears in the construction of this relative Fark-Fontaine disk. And we have just done the dagger sequenings along like Frobenius translates, like Frobenius via Gauss components just corresponds to the shift here on this product. And so we have just secant at like along one divisor on all its positive, non-negative Frobenius translates. So that's why some of this coincides with this rather explicit push-out description. So I want to, that won't really play any role in everything I will say in the rest of my time, but it's really the correct point of view when you try to, maybe we'll discuss this at the very end, when you try to define this analytic prismatization integrally. You have to use this kind of modified with vectors construction, and they do not have a simple geometric description as the one which is on the middle board. And that's also, by the way, the reason why in my definition of delta spaces, I require that curly X is a Berkovich space. And not, maybe, I could a priori have taken an arbitrary Gelfand stacks, but I really want that the push out is really given by locally by the fiber product of rings, so that it really matches with this description that we get from bit vectors. So that's a technical point, but okay, so maybe I should make a small break. Let's continue. Right, so let me introduce a notation. So I will let unstack delta be the category of like sheaves for the Schrick topology on the category of delta spaces. And here, when I say Schrick topology, it's really the Schrick topology on the underlying Berkovich space. Okay, and so like in the p-complete setting, we now have like a realization functor from this category of analytic delta stacks to Gelfand stacks. I will use the same notation, realization, which is colimit preserving and sends sending a delta space, or the functor co-represented by a delta space S, X to X. Okay, so that's some version at the level of sheaves of this of the forgetful functors from delta rings to rings, and by what we have this proposition, I know erased, but I had stated before the break. This has a left adjoint. Given by so sending sorry, maybe I don't want to let me say it like that. So by proposition before, it can be sort of explicitly described as follows. It sends so this realization functors sends a delta analytic stack Y to so it's a Gelfand stack, so I can also think of it as a stack on nil perfectoid rings. So it will be the stack which sends T, which is G spec A, where A is nil perfectoid. to y evaluated on this initial object, initial delta space. And that's a priori not necessarily a Gelfand stack, so you have to take a priori the Schritt-Schrittification of this. Okay, so that's maybe the main purpose of this proposition. I had stated that when you have some functor which is naturally defined on delta spaces, you want to realize it as a Gelfand stack. That's what we will do to get the prismatization. Well, you get a functor of points description on nil perfectly rings, which is given by that. Except that it a priori involves some Schiffifications, but we will see that in the examples we care about for the prismatization, this is actually not necessary. Okay, but so that's, I hope, clearly analogous to what I had stated at the very beginning, using instead this analog. So the way you get this usual prismatization using Witt vectors out of the functor, like the prismatization as a functor on delta rings. Okay.
Keys for the Schritt topology on delta spaces, like how are you assigning? Like usually you would assign some category of quasi-coherent sheaves, I guess, to every object in that category, and there would be some six-functor formalism.
Sorry, can you say that again?
I'm just trying to make sense of the state.
So, okay, the topology is, I say a morphism Sx to S prime X is a Schritt cover if it is on the underlying Berkovich spacing. So
okay,
if the map X to X prime is a Schritt cover of Gelfand. Okay, that makes sense.
Yeah, it makes sense.
So it's a bit like when you define the topology on the category of delta rings, it's always like the topology on the underlying ring. So that's analogous to that. Okay. Before I go on, I also want to, everything I'm explaining now is sort of motivated by this analogy with a theory of p-complete prismatization, but it's also visibly quite close to the theory of arc stacks, right? Because we've seen that this category of delta spaces, or even perfect delta spaces, it's sort of a generalization of perfectoid rings, of perfectoid spaces in characteristic P. It contains it as a full subcategory given by these classical delta spaces.
That's quite different from the sort of classical setting, right? Because perfect prisms are perfectoid rings, but here perfect prisms are, perfect delta rings are perfect rings, and perfect prisms are perfectoid rings, and it seems like...
Yes, that's right, yeah.
Okay, great.
Yeah, indeed. And so this relation, so that means that the theory of analytic prismatization, it's in some sense it's an analog of the theory of prismatization of p-adic formal schemes, but it's also, you can also think of it as some kind of refinement of the theory of diamonds and arc stacks. So it's kind of combining these two important aspects of p-adic Hodge theory of in recent years. And one way to make this relation to arc stacks a bit more precise, it will be really analogous. So remember, on Monday we had these adjunctions. We had this perfectoidization functor, and we had this left adjoint, denoted like this, and we had a right adjoint, which was the Ramstack functor. And the toy model was like stacks on FP algebras or stacks on perfect FP algebras. And you know the situation for delta spaces really look completely analogous to, quite analogous to this toy model. So maybe the precise statement is that the functor, we have a functor from, so I don't have really a good notation. I denoted diamond FF from analytic delta stacks to arc stacks, which basically is just sending Y to its restriction to to classical, not perfect, to classical delta spaces. So it's the arc stack which sends S to Y evaluated on S, the punctured Fark content X. So this has both a left and a right adjoint. And I want to, for later use, I want to give names to these adjoints. So the left adjoint is and we denote like this. And so it's so left adjoint, so it's co-limit preserving functor, sending S sorry, okay, and the right adjoint sends an arc stack Y well to and this right adjoint I also want to give it a name. So this will be denoted like this. Okay, sorry for all the notations. So this both adjoints are fully faithful, and what I will make use of is the following, just the following fact. So maybe to make that, so you can, so okay, these left adjoints, they go from arc stacks to these delta analytic stacks, and then I can furthermore realize them as Gelfand stacks. So after realization, well, this d star ff functor is just the same as before. It's the one I had introduced in a remark in the first part of the talk. So I explained that this construction of the punctured Fark Fontaine dx satisfies, like, sends arc covers to Schrick covers of Gelfand stacks and can be extended as a co-limit preserving functor from arc stacks to Gelfand stacks, and that's exactly what the same functor. So that's why I chose this notation. Like, it's compatible with the notation I had before. And for the other one, if I take this d star ff the RAM and then I take its realization, well, it's basically a construction we saw on Monday. So it's just this this functor which take a fiber product with the arc stack of QP over the arc stack of FP and then take the RAM stack. So that's on Monday we saw this construction, but we in addition we took a quotient by Frobenius, and that's what we call the Yodo-Kato stack. Right, and so just by adjunction, this means that if Z is now any delta analytic stack, I get a composition like this. So I have d star ff for this Z diamond of ff going to Z, going to d star ff. And this is just, sorry, that's really for, I should write really. Do I want to write like this? Yeah. Maybe everywhere I now take the realization, so, sorry. Write like this. Okay, and this composition is just this is a Gelfand stack, and this is just the natural map from this Gelfand stack to its Durham stack. And now this is factoring through the realization of Z. So maybe let me give a name to this composition. Let me call this star. I will apply this in a moment for a particular Z. Okay, so so you can think of this analytic delta stacks as some kind of maybe refinement of the category of arc stacks. And so now finally I can come to the definition of what a prism is. So if Sx is a delta space, I will define a Cartier divisor. So as on Monday, whenever I say Cartier divisor, it's always meant in the like as a generalized Cartier divisor. So it's a Cartier divisor on X. It's said to be of degree 1. If it's pulled back to via iota, it's pulled back to the Fark-Fontaine disk of S is of degree 1 in the sense of Fark-Scholze. Meaning that it corresponds to some untilt in characteristic 0 of S. So there is, for perfectoid Fark-Fontaine, for these Fark-Fontaine disks, punctured Fark-Fontaine disks, there is a notion of degree 1 divisors. These are exactly the one corresponding to untilts. And if I have a generalized Cartier divisor on my Berkowitz space X, I just say it's of degree 1 if it is so after this pullback by iota. And a prism, I should really say a rational analytic prism, but I will just abbreviate this to prism, is a triple, or really like, okay. As usual, I just skip from the notation the iota and the Frobenius, where Sx is a delta space. And D on X is a degree 1 divisor. Okay, so now let me denote by, really I'm just repeating what I said at the beginning in the integral case. So QP prism will be, like lower prism will be some analytic, so it will be an analytic delta stack, which is sending S, X to, like degree 1 Cartier divisors on Sx. And similarly, more generally, if X is a Gelfand stack, we define X lower prism, again as an analytic delta stack, just as a functor which sends. So it will be defined as an object over QP prism. And so if you have a prism, and then you send this to like maps from D to X. Okay? And then to define the analytic prismatization itself, you just apply the realization functor. But for this, I will put some restrictions. So I will assume that X is a Berkowitz space over QP. Then you define, and I will comment on this assumption later, X upper prism. So this will be the rational analytic prismatization of X. as the realization of X lower prism. And so claim is that it is a functor, so it sends T, which is G spec A nil perfectoid, to degree 1 divisors D on xt with a map from D to. No, sorry, not curly X. Sorry. That's a curly X, that's like the delta space associated to the nil perfectoid ring A, and this is my Berkovich spaces. And the assumption that X is a Berkovich space is there somewhat to ensure that this is a correct functor of Poincare description. That there is like this schiffification that appears in general, as I mentioned before, is not necessary in this case. I will explain why in a moment. Okay, and then once you have defined the prismatization, you can also define some variants. So you define the perfect analytic prismatization I don't know why we chose this stupid name, xdiv1 tilde, but okay, I will just stick to it. So any analytic delta stack, it's a stack on delta spaces which are endowed with a Frobenius. So any such stack comes equipped with a Frobenius. And so you take the limit Frobenius perfection of X prism. So that's the perfect analytic. Well, sorry. I decided not to put this adjective, so let me just say perfect prismatization. And you also define xdiv1 as the quotient of this perfect prismatization by Frobenius. You know, you made Frobenius on isomorphism, so you can take this quotient. And then one last Gelfand stack that you can define, which is important. This is the so-called hot state stack. To make sense of it, you need first a small observation, which is that, so that would be part 5, I guess. So first observe that there is a map, a natural map. So pull back along 0 times t, which is just t, mapping to n times t, mapping to xt. That was part of the construction of this delta space associated to t. If I pull back my degree 1, a Cartier divisor of degree 1 here, I get a generalized Cartier divisor on t. And the moduli of the functor sending T to degree 1 to generalized Cartier divisor on T is represented by A1 mod GM, and so that gives me a map, induces a map, X prism, well, which it's really like already like factoring through the prismatization of spec QP itself to A1 mod GM. And one defines the analytic hot state stack just as a fiber product with BGM. Okay, so this is like the various stacks I want to consider.
From earlier, you were saying that analytic stacks with a delta structure, or analytic stacks delta, is some sort of refinement of perfectoid spaces and characteristic P, or sorry, arc stacks spaces and characteristic P. Is it correct that you have that there's a fully faithful functor that arc stacks is a localization of analytic stacks delta under the constructions that you're explaining?
So these two adjoints that I have described, they are both fully faithful.
So they're fully the localizations.
Yeah.
Right.
So it's like this adjunction on top of the board, like this hat functor and this the Ramstack functor, they are also both fully faithful. Okay, so some quick remarks about this definition. The first is that if you have any prism, then you have a map, natural map from X to, okay, I will just write QP prism, what I should denote really by G-spec QP prism. And that's sort of just obvious from the definition. This is just a realization of, that's just obtained by, so you have a map from S, it's from the delta space to a QP lower prism, because that's the choice of D is exactly the choice of a degree 1 Carty divisor is exactly what it means to have a map to QP prism for a delta space by definition. And then you just take realization, and the realization of such is by definition just the underlying Berkovich space. And also by definition, QP upper prism is a realization of this. Right? So you have such a map. So that's completely analogous to, in the integral theory, if you have a prism, then it gives you have a natural map from like its formal spectrum of the underlying ring to the prismatization of ZP. So the same mechanism here. So for example, like one example is I can take this this example we had before. Of the cyclotomic delta space, and there I have the ideal which is generated by like this Q analog of P. So I just take the divisor which is defined by this ideal QP minus 1, Q minus 1. So that's what I will call the cyclotomic prism.
P sub Q, right? Not Q sub P.
You
mean P sub Q?
Ah, yeah, thanks. Yeah. But of course, another maybe more trivial example is whenever you have a perfectoid space in characteristic P and you take the relative Punktort-Frankfurten-disk over it and the degree 1 divisor given by some untilt. That's also an example of a prism. And because of this remark 1, exactly like in the integral theory, you can also make sense of the relative prismatization. So if, again, if you have a prism, and X is living over my Berkovich space X is living over D, now I can define its relative prismatization relative to curly X. I should really write relative to S, curly X, D, but I just use the standard Abusov notation. And this is just X prism times D prism times X, using the map from X to D prism, which is given by 1 by this the previous remark plus the identity map from D to D. Okay, so like by previous remark, I have a natural map from curly X to QP prism, and it upgrades to a map to D prism because I have a natural map from D to D, just identity. So okay, you can make sense of relative prismatization. That's expected, I guess. And so in the rest of today, I'd like to discuss a bit the geometry of the prismatization. So maybe the first remark first observation is that if I take if X is in fact, any Gelfand stack, then this X lower prism as an analytic delta stack, when I apply this functor that I have defined, where it is here, this functor to arc stacks, so the one that I denoted diamond Fark Fontaine. So as an arc stack, it's really just X diamond. So this analytic prismatization of X as a delta stack, it's really, it's the underlying arc stack, so to say. So meaning the functor that this prism FF functor applied to it, it's really just the usual arc stack associated to X. That's just by looking, basically unraveling the definition of what you are doing. And so this means I can rewrite in a rather nice way this composition here. So star becomes now the following. So you have, okay, so in the middle, if I take realization, so I will apply star for Z, which is X lower prism. So by definition, its realization is the prismatization. So in the middle, I have X prism. And on the left, I have the relative Fark Fontaine disk construction for the diamond of X. So just the thing you get by descent from the perfectoid case. And on the right, you have its Durham stack. Which again, just because the Durham stack only depends on the associated arc stack, and the arc stack of this is just this fiber product. It's just the same as X diamond times MRQP Durham.
Arthur.
Yeah.
Sorry about this. I think, is there a claim being made in this implication of the star? Sorry, I kind of missed this. So I guess there's like, in the middle board, the star. Is there a claim being made?
No, I just say that you have such maps just by adjunctions.
Yes.
And this composition is just, this is the right term, is just the Durham stack of the left term. And
okay.
Maybe I'm just claiming, like this composition is just a natural map from this Gelfand stack to its Durham stack.
Okay, cool. So it's just a definition.
Right, yes. And so here you see that you have this relative Fark Fontaine disk mapping to its Durham stack, and this factors through the prismatization.
Cool, okay.
So note that the left and the right term, they only depend on the underlying arc stack of X. So on some kind of the underlying topological space, if you like. But the middle term does really depend on X as a Gelfand stack. So on the, like really as a rigid analytic space.
I think it just missed. Could you say again what the X diamond FF is? I'm just slightly trying to parse the equation up top.
So diamond FF is this, that's really stupid notation for this underlying arc stack. So basically you have a functor defined on delta spaces and you just restrict it to classical delta spaces. And you see you are basically, so classical delta spaces is just the same as category of perfectoid spaces of characteristic P, and you are looking at degree 1 Cartier divisors on relative Fark Fontaine disks over perfectoid spaces, and that's by definition of degree 1 divisor in the perfectoid case, that's the same as untilt. And so you see that this is the usual definition of the diamond. And also, you can, of course, this also just like in this left and right terms, they are all perfect. Frobenius is an isomorphism on that, so this would also like naturally factor through this perfect analytic prismatization. And if I take the quotient by Frobenius, then I get Fark Fontaine of X diamond mapping to X div 1. That's by definition the quotient by Frobenius of the perfect prismatization. And then the thing on the right is Fark Fontaine X diamond RAM, but this is what we call last time the Yodo-Kato stack. So I will use quite a lot this. So I want to give name to this map. This will call alpha X, and this will be called beta X. And basically, beta X will be used to analyze the geometry of the div 1 stack, or its variant of there will be used to analyze the geometry of the prismatization today. And this will play an important role in my last talk. This, like we will compare perfect complexes on both stacks. Yes.
Is there an analog of what you're writing in the integral?
I'm not sure. I think if you take the perfect prismatization in the integral case, it's already quite close to being this. So yeah, I don't think so. Okay.
Can I ask one more question? Sorry, maybe this is related, but or you explained it, but so you said that taking the de Rham stack is like kind of like taking the underlying topological space in this theory. That was
maybe more like this perfectualization functor. I think of it as taking the underlying topological spaces. Topological space. Okay, one reason to say that is I wanted to mention this next time. There is some kind of complex analog of everything we do in the p-adic case, and in this situation, the category of arc stacks would really be just replaced by the category of condensed anima. And so, in this way, that would really be the complex analog of this perfectualization functor would really be something like taking the underlying condensed anima.
so maybe just hold up. So maybe this is implied by what you wrote, but so is this map that you defined in star, that map is an isomorphism on de Rham stacks? So
yeah, that's true. Yes, maybe I should also have said that. That's also the same as the de Rham stack of X prism.
So X prism is some sort of enhancement of the Fark-Fontaine stack of X. I mean, in some diagonal potent directions, the first approximation.
Yes, that's one way to. Yeah, that's right. So we will see that X prism is quite close to its de Rham stack. So that's what I want to. Basically, because these delta spaces attached to nil perfected rings, they are really quite close to the relative Fark-Fontaine disks attached to the dagger reduction. Yeah, but maybe another remark also, why X Berkovich space? Why did I restrict myself to... So, okay, sorry, there I should, because of the way I set my definitions, I should... That's always true, but because I only define the prismatization in the, okay, for Berkovich spaces, let me also make this assumption here. Why do I put this assumption? That's because, what do I want to say? Yeah, this delta space attached to a nil perfectoid, it was defined as a push out. And so this means if I have D, if D is a degree 1 divisor on curly xt for T nil perfectoid, then you can also describe it as a push out of, like you have its restriction to n times T, and its restriction to, well, restriction I really mean like a pullback, and sorry, D, and its restriction to this Fark-Fontaine disk of T flat. And because that's really a push out in Berkovich spaces. So that means that, Okay, so this when I take this X prism, and I could of course define for any Gelfand stack, I can make sense of this X over prism. I could take its realization, but in general, I would maybe just only have a map from here to. So what is a functor which sends T to a degree 1, a generalized Cartier divisor on T together with a map from this divisor to X. It's exactly what I introduced last time as a cone construction of X. So what I get is, in general, is just a map like this, product of X cone, like n copies because I have n copies of T. And then here I take a fiber product over the product of the Ram stack of the cone. And here I have just again what you get is d star ff of X the Ram. Because that's, well, again, unraveling the definitions, that's what you get as a, if you just look at this piece. Okay, but no, because if X is a Berkovich space, no, in fact, this is in fact an isomorphism. So if X is Berkovich, so this is my X prism, and this is an isomorphism. And in particular, I mean, you see this is already a sheaf. I mean, that's not completely obvious for this part, but that's part of the results the result we prove about the Ram stacks. So no sheafification is necessary, but even better, as an output of this, you get a nice description of. So let me state this as a proposition. X is a Berkovich space. Then you have a pullback square. X prism goes to it's the Ram stack, which is this. So that's exactly the map that I have on the right in my diagram star. I did not give a name to it. And this maps to the product over n of X cone, and this map to the product over n of X cone. And that's a pullback square. I mean, I'm just repeating what I wrote there. Another way to say that is that this map is dagger formally et al. Oh, sorry, this vertical map is dagger formally et al. Because here the vertical line on the left, the vertical line on the right is just what I get by passing to the Ram stack from what I see on the left. So this means that another way to say this is just to say that this is dagger formally et al., meaning that it is just pulled back from the map it induces on the Ram stacks. And things get even nicer when you pass to, okay, and for perfect prismatization, of course, you have the same statement, except that you replace natural numbers by Z. And then you pass to quotient by Frobenius, and the diagram gets even simpler. So also, and you get a pullback square, so X div 1 goes to X Yodokato. So that's my beta X up there. Goes to X cone. So now, because I took the quotient by Frobenius, all these copies of the cone get identified to each other. And then I have X cone. And this is a pullback square. Okay, so to be compared with what we saw last time, that this filtered the Ram stack construction, I can also, I explained that you can also write it in a similar way. That's some kind of relative to Ram stack construction. So, except that I explain this description of the filter the Ram stack and as just pulled back from the map from the cone of X to its the Ram stack. And here you see it's a quite similar thing, except that here we use a rather simple map, but here it's a more complicated construction involving this Yodokato stack. All right. Yeah, and maybe a small picture. So again, using the same trick. So X prism the RAM. It's the same as this Farg-Fontaine X prism. Sorry, D star. The RAM, and so you can use a radius map again you have there, and so you have a radius map kappa from X prism to 0 infinity. And if I try to make a picture now, it looks something like this. So it's generically like this horizontal map on top in my proposition is an isomorphism, but what's happening is that I have again this, so Frobenius is again going like this. I have 1 over p, 1 over p square, p, and so on. But now it's kind of reversed compared to what we had before. So here I see the de Rham stack of X. Here I also see a de Rham stack. But here I see the Hodge-Tate stack. And then when I go the negative direction, it also repeats. So I also see the Hodge-Tate stack. Okay, so it's basically the de Rham stack of this Farg-Fontaine disk, except that I have this Hodge-Tate divisor, and then all it's translates in the negative direction, where I do a modification. And that's a bit useful to understand how this X prism looks like. So let me just finish by stating the proposition which describes this stack. So the proposition is that so X is again a Berkovich space. So the map, that's quite, I mean, what I will say is obvious if you believe in this picture. So the map X prism to the RAM stack of the Farg-Fontaine disk over X diamond is an isomorphism over 1 infinity. Well, when I say over, it is via this map kappa. And this map is, again, is the one that we have already considered before. And in particular, I have a Frobenius induces an isomorphism between X prism restricted to like the fiber over this interval 1 infinity and X prism over p infinity. And if you take the quotient by Frobenius, by which I mean like the co-equalizer, you just get the Yodo-Kato stacks there. But on the other hand, if you now look at the map from the perfect prismatization to X prism, so now this one is an isomorphism on the other part of the picture. So it's an isomorphism over 0p. And so Frobenius is in particular also Frobenius is an isomorphism, induces an isomorphism between so what do I want to write? X 0, 1 prism and if you would take again the similar co-equalizer, then you would get this D1 stack. Okay, so basically this X prism, one way to say that is that it's like it's a push out of, so over this, okay, so I will try to get that right. So I want to do it, so over X 0p, it's just the same as this perfect analytic prismatization. And then on the other, on 1 infinity, it is the same as the RAM stack of the relative Fark-Fontaine disk. So now it's over 1 infinity. And so I have, okay, this is like P. This corresponds to 1. So here I have something here. That's a part where it's a perfect prismatization. And somehow on this part now, it's the same as the RAM stack of the Fark-Fontaine disk. So I glue on the intersection where it is, well, the two are identified. Let me write like this, but this is also identified as D star fx diamond 1p. So this tells you the following basic things, that to understand the prismatization, this rational analytic prismatization of a rigid space or a Berkovich space, you really need to understand this perfect analytic prismatization and this like the RAM stack, Fark-Fontaine, the RAM stack construction. Or because both are perfect, you can also pass to the quotient by Frobenius, and really you have to understand the theory of Yodo-Kato stack and the theory of div1 stack. Theory of Yodo-Kato stack, I won't really discuss it in the next talks. My plan for the remaining lectures is, next time we will really focus on this div1 stack, and I will try to give some explicit examples for SPA-QP first of all, but then also for the rigid analytic multiplicative group. And in the last lecture, I will explain how to use the pullback along the map alpha x to describe perfect complexes on this stack to perfect complex on this relative Fark-Fontaine curve. And we will see that this is basically the stacky formulation of the main results of geometric sense theory. Okay, that's all for today.
So this may be a very naive question. Do you consider, for example, analytic prismatic cohomology by defining still the push forward of the structure sheaf? And does it carry some natural filtration since the stack is naturally filtered?
Okay, so the filtered version of the prismatization will be the topic of Maximilian's lectures. But yeah, of course, it's a good question. What's the coherent cohomology of this stack? So what's the cohomology theory that it is geometrizing? And again, this push-out description tells us that it's glued by, it's some kind of like what is called a Stuka, so it's glued from something like the cohomology of this stack and the cohomology of this stack. And this is, like as the notation suggests, and as I briefly mentioned on Monday, this is computing this Yodo-Kato cohomology for rigid analytic spaces, as defined by Kolmez and Nisiol, maybe some other convergent version. And what is this stack geometrizing? Well, in fact, I just made a much stronger claim. I claim that pullback along this map, say for X, a smooth dagger rigid space, is an equivalence of category. So in particular, cohomology of these stacks are the same, but the cohomology of this relative Fark-Fontaine curve is exactly pro-etal QP cohomology. So, like the cohomology of the structure sheaf on the prismatization is some kind of Stuka which is gluing pro-etal QP cohomology and Yodo-Kato cohomology. That's
So can I just have a small question? So I didn't, maybe I got lost how you get the product of why it's a product and not like some sort of, why does it become a product and not a co-product? And well, maybe I guess the map is to the product, but could you say again what is the map from X prism to the product of X cone?
It's just given by the restriction to. Sorry, did I get myself confused? Just a restriction to for each integer n. I fix n, and then I get just. I just get the restriction of d to small n times t.
And sorry, X cone, does that live? I mean, that has to X prism maps to QP. It maps to QP prism, right? It maps to the remembering the divisor.
X prism maps to QP prism, yes, and QP cone is just A1 mod GM.
QP cone is okay.
Yeah. So you get like on QP prisms, you get many maps to A1 mod GM. I mean, because you can pull back instead of pulling back to 0 times t, I could also pull back to n times t for any integer n.
Sorry, but anyway, just to make sure I understand, so the statement of the proposition is that this diagram that you wrote is a pullback.
Yeah, that's a pullback square. Yeah, that's what I was saying. Or another way to put it, as I said, is saying that this left vertical map is dagger formally étal.
So if there's no more questions, let's thank Arthur-César again. So the next talk is Friday at 4:30, but in the previous room.
Wherever you need to go. This is yours, I think.